Right, we'll get started in a minute or two. Just wait to see if other people are joining today. Give it a minute. Cool, might as well get started. So, identifying functional groups using test tube reactions. So, how to identify alkanes and alkenes? The test is adding bromine water, which is an orange solution. If it's an alkene, meaning double bond present, the orange solution will turn colorless. If there is no double bond present, the orange solution stays orange. And again, this is due to the double bond undergoing an electrophilic addition reaction, where the bromine is added, forming a haloalkane. Easy. So it's an electrophilic addition reaction. So you can see, again, we'll cover a little bit more of that kind of in our next couple of sessions. It's weird that we're going in this order, starting with functional group identification and then moving towards the actual content, but just recalling that this is a electrophilic addition reaction across this double bond. We'll talk about that later. Yeah, so bromine is decolorized in the presence of alkenes. Identifying haloalkanes, you can do that by warming with dilute sodium hydroxide, which then breaks those haloalkanes from it's basically a substitution. So you do this so that the halogens ions become free, so they're freed. Then you add acidified nitric acid and silver nitrate. So you add acidified silver nitrate with nitric acid, and then you add dilute ammonia as well as concentrated ammonia, just to be able to differentiate. But this is the main part of the reaction. This gives you the colored precipitates. Electrophiles are positive, but bromine is negative. How is it acting as an electrophile? It is not acting as an electrophile. The double bond in the alkene is acting as the electrophile. So that is where the electrons from the negative Br ion that is an electron dense region. And the bromine basically, so you can see that because of this high electron density, that pushes electrons away from one of the structures, from one of the bromines, and towards the other bromine, creating a dipole within the bromine molecule itself. That's electrophilic addition, simplified. But yeah, you need to remember these colors. So chloroalkane will form a white precipitate, bromoalkane will form a cream precipitate, and iodoalkane will form a yellow precipitate. And then in ammonia, the chloroalkane precipitate dissolves immediately with dilute ammonia. The cream bromoalkane dissolves with concentrated ammonia. And then the yellow iodoalkane is insoluble in both dilute and concentrated ammonia. And remembering those is very important for your exams. No, there is no copies of this presentation being handed out, but I'll give you time to write this bit of content down. Because again, very important content, so I'll give you a bit of time to write. Second or two to write this down. Is the sodium hydroxide used to remove carbonate ions? No, the sodium hydroxide is used to remove the halogens. It's basically used to free up the halogens by substituting this hydroxide ion instead of the halogen ion, basically. That's the idea. And again, a nucleophilic substitution reaction. So this is an explanation of this. A nucleophilic substitution reaction occurs between the hydroxide ions from sodium hydroxide and the haloalkane, which then releases that halide ion to be identified. Hi, are we doing spectroscopy today? Yeah, pretty much immediately after this. This is just the basics for this topic. Identifying alcohols, you can warm them with acidified potassium dichromate, and this will create a orange to green color change only with primary and secondary alcohols, but does not react with tertiary alcohols. And again, this is because primary alcohols and secondary alcohols both get oxidized, but tertiary alcohols are not oxidized any further. Give me a second to write this down. Is an indicator used? No, the indicator is inherently within it. Okay, identifying aldehyde. So you warm the aldehyde with something called Tollens reagent. That forms the silver mirror. The reason is because of a reduction reaction occurring to the silver ions. So silver ions are reduced to silver solid, but the aldehyde is then oxidized to form a carboxylic acid, which means that this reaction can't occur with carboxylic acid or tertiary alcohols. It could still work with primary and secondary alcohols though. The other test is using Fehling's reagent. Fehling's goes from blue to brick red. Again, Fehling's solution is an alkaline solution of copper 2+ ions dissolved in ammonia. Can anyone who does biology potentially identify what Fehling's is the same as? Yeah, well done. Fehling's is Benedict's reagent, but just different. Again, it works in exactly the same way Benedict's reagent does. It's a solution of copper 2+ ions, and it oxidizes, reducing sugars. So it works as an oxidizer, basically, while it itself is getting reduced. And yeah, the copper ions are reduced to copper oxide, and the aldehyde is oxidized to make a carboxylic acid. The other test, again, is a acidified potassium dichromate test. And again, you expect a blue to orange to green color change. And again, this is due to the oxidation of the aldehyde to a carboxylic acid. For Fehling's is a copper 3+ to copper 2+, so it's a reduction Yes. So copper 3 plus goes to copper 2 plus. No, copper 3 plus goes to copper 2 plus goes to copper 1 plus or Cu plus. Yeah. Not copper 3 to copper 2. And ketones, again, you basically put them through all of these reagents and you see no reaction. This is because ketones cannot be oxidized any further. Carbonate test is using lime water. So you add lime water, so you add a carbonate to a carboxylic acid and bubble any gas produced through lime water. The reason is because carboxylic acids are acids, which means that to any carbonate, they will produce carbon dioxide because they'll produce a salt, water, and carbon dioxide. And again, carboxylic acid, again, the other test for it is going through all of the other oxidizing tests. And since carboxylic acids cannot be oxidized any further, they will not undergo any further testing. Okay, cool. Mass spec. So mass spec and then IR spec. So we'll go through both of them. So mass spec is can be used to determine the molecular mass and molecular formula of a compound. They work under the same principles as the time of flight mass spectrometer we discussed in one of our previous earlier lessons. So what I'm going to do is I'm actually just going to skip most of this, and I'm going to explain it kind of at the end, just quickly recap on it. I'm not going to go through too much detail. If you want to know how a time of flight mass spec works, the best bet is to kind of go watch the recording of the first ever kind of lesson that we did. We talked about time of flight mass spectrometers there. So what you do is you get your sample, you vaporize it. So you take your sample, call this the sample, gets vaporized. So turns to gas. It enters the machine. Once it enters the machine, it becomes ionized. So the vapor becomes ionized by basically adding a proton or removing an electron. Either way, you form lots and lots of positively charged ions. At step 4, what we're doing is we're basically deflecting. So we're passing it through a magnetic kind of field. It's basically a magnetic force. So molecules pass through magnetic force. This gives same kinetic energy. That's the idea, is so that molecules all have the same kinetic energy. And if you remember what I said about kinetic energy, so kinetic energy is linked to a half mass times velocity squared. So if the kinetic energy is equal, but the mass is going to be different, the smaller the mass, the higher the velocity, which means that smaller molecules are going to pass through this time of flight mass spectrometer much quicker, which means that they're going to get to the end of the mass spec faster, which means they're going to be detected faster. So basically, what's happening is that the kinetic energy is kept equal, but the mass and the velocity, the mass is going to be variable, which means the larger the mass, the smaller the velocity, which means the slower the particles are going to move. And then for the rest of it, they kind of just drift through. Particles continue drifting through and then are detected by the computer. That's kind of the idea. And then the computer generates kind of an image or a graph that will give you the mass spec. So If you want to write this down, I'll give you a minute or two. Got some questions in the chat. OCRB, this is AQA, but actually this correlates to OCR as well. So there is in both specs. I know you need to know this for OCR because that was the one I did. Will we receive a call recording of this? Yeah, the recording will be posted onto YouTube. Well, it should be on YouTube right now as well. You can watch it live on YouTube, and then it'll stay on YouTube forever. So you can watch it through that. Cool. So basically, that's kind of the idea, that the ions just drift through and then become detected. Sorry, being given a question by Abigail, do I need to know this for OCRA as well? It doesn't say anything about the ins and outs in my textbook. Yeah, you do need to know this for OCRA. Time of flight spectrometers are on the spec, and I've seen them in exam questions before, which is why it is better to kind of learn it, because it is something that they can ask. Usually they'll ask that as an AO3 question though. So they'll ask it as more of a kind of applied knowledge. So maybe it might not be in the spec as a necessary piece of knowledge, but I have seen exam questions on it. Yeah. So again, the mass spec for ethanol. Remember, whenever you're looking at spectroscopy questions, the only peak you're really looking at and the only peak you're really focusing on is the molecular ion peak. And so they're the last peak. And that basically, the molecular ion peak, the value that is at, tells you your MR. So that's what you need to kind of know. So M plus peak equals MR. If you understand that, that's kind of how you approach that for any question that you're given related to spectroscopy. And then the height of this peak then relates to its relative abundance of this isotope of the molecular ion. You don't need to worry about that much. And again, the MZ value basically just means the molecular mass of that compound. So let's think about this. So chlorine exists as Cl35 and Cl37 in the ratio 3:1. So what kind of peaks do you expect to see? If people want to write this in the chat, take a second. $70. So 1 as for Cl35, Cl37, Cl35, and Cl37. Okay, we've got a couple of different answers here. So I would expect to see 3 peaks. So a peak at 70, a peak at 72, and a peak at 74. And the ratio of these peaks, which will exist in the ratio of 96 to 1. The sum of these ratios, again, will be 16 times 2. So there'll be 24 CL35s, 8 CL37s, which gives them, then works back to give you the ratio of 3 to 1. Basically, it's just a peak at 30, a peak at 70, which is for the 2 35s, a peak at 72, which is a 35 and a 37, and then a peak at 74, which is 2 37s. That kind of makes sense. So those are your 3 peaks there. Okay, let's go through the last bit of content, infrared spectroscopy. Before then, I'm going to stop for a bit of questions, if there are any questions so far. So I'll open it up to questions. Any questions at all about this content? For the previous questions, how did I find the ratios? Cool, I'll explain that quickly with the whiteboard. So basically, the ratios are 3 to 1, right? Which means that there is a 1 in 4 chance that the molecule that you pick is going to be a Cl37, which means that there is a 1 in 4 times by a 1 in 4 chance that you are going to get 2 times Cl37s, or a 1 in 16 chance. There is a 1 in 4 chance that the molecule you're going to pick is a Cl37, and a 3 in 4 chance that the molecule you're going to pick is Cl35, which means that you've got a 3 in 16 chance of getting a Cl35 and a Cl37. But that is not the only configuration you can get that kind of probability, because you could pick a Cl37, 35 first. So you've got a second way of doing that. So the overall probability of picking a Cl35 and a Cl37 is 3 in 16 plus 3 in 16, which is 6 in 16. And then the probability of picking 2 Cl35s is 3 in 4 times 3 in 4, which is 9 in 16. Now your ratio will be 1 in 16 to 6 in 16 to 9 in 16, which is a 1 to 6 to 9 ratio, because it just means that total is out of 16. I will get back to this question about study techniques, because again, I will kind of, after we've completed IR spec, I will open it up to any study questions about kind of your study techniques and study skills. But infrared spectroscopy. So IR spectrum basically is based on molecules absorbing infrared waves. And infrared waves are a form of electromagnetic wave. And when infrared waves is passed through a compound, the bonds in those in the molecule is going to absorb some of this radiation. The amount of energy this bond absorbs is different for the different bonds that you have, because each bond has different capacity for absorbing waves. And so the amount of absorption can tell you the type of bond that is present in a molecule. And it can tell you, therefore, the functional groups present in a molecule. Now, you get given these wave numbers, so you don't have to memorize them. So all you're doing is when you're given an IR spectra, all you're going to do is you're going to say, okay, I see this molecule, or I can see this peak. this peak means this wave is present. That's kind of it. That's what you're kind of trying to do. The fingerprint region between 500 and 1500 centimeters is unique for all molecules. It represents the wave numbers absorbed by the carbon-carbon and carbon-oxygen bonds, as well as the vibrations of the whole molecule as a whole. Can I go back to the info page? You mean this page? Or do you mean this page? Sorry. Okay. Yeah, I can wait a second, let you write this down. At the end of this bit, I think, because we might have some time, what I'm going to do is I'm going to actually talk you through a 9 marker, and I'll do it, and I'll show you how kind of you want to be doing a 9 marker. So for people who are looking to stay behind for some exam technique style questions, I'll show you kind of how to do that. We'll kind of go through that. What is wave number? So the wave number is basically just the wavelength, or basically the amount of energy that the bonds are absorbing. Okay, so fingerprint region is unique for all molecules. So you can't really use the fingerprint region to identify functional groups, which is why you'll notice that most of these functional groups are beyond that fingerprint region. The fingerprint region, although it is useful for identifying the length of molecules, you won't need to do that because MR spec will give you that. But the fingerprint region will help you identify explicitly kind of carbon-carbon and carbon-oxygen bonds. Realistically, the IR spectrum, the best way to think about it is it's just the amount of energy being absorbed. So you just need to therefore look at the wave number of these peaks. So if you see this broad peak between 3,230 and 3,550, you're thinking OH group, carboxylic acid. And the best way to do that, again, is just to compare to your information sheet. An OH group in acids produces a strong broad peak between 2,500 and 3,000. A carbon-oxygen bond, carbon C double bond O, a strong 80 and 1750, and that probably will tell you it's an aldehyde or a ketone. If you see that in alongside the broad peak, then you're thinking carboxylic acid. So if you see this broad peak around 3000, you're thinking OH group, probably a carboxylic acid. Okay, let's have a go at this as together. So you guys, if you want to put it in the chat, what are your thoughts on the functional groups in this molecule? C double bond group, O group, yeah, I can see that. So that's this kind of broad peak here. And an acid group, well, yeah. So quite complicated, but there is a signal here. So this signal kind of, for me, indicates the broad peak OH group. And there is a C double bond O here, which is a separate C double bond O group, which means that this is not a carboxylic acid. Remember, for a carboxylic acid, you want the C double bond O group to be sort of closer behind, about 2,500 to 3,000. But for an OH group in an alcohol, you're thinking it's going to be further along at about 3,230 or 3,550. Again, they're both broad peaks, but it's where they're located. And since this is kind of further along, I'm thinking that it's probably going to be an alcohol and a ketone or an aldehyde group as well. We're not going to talk about this because this is amine identification, but yeah. And obviously, people, you should know that if it's infrared spectroscopy, there is short wavelength ultraviolet, and the infrared waves get absorbed by the Earth, and some of it gets re-emitted, which can absorbed by greenhouse gases. If it's absorbed by greenhouse gases, this can then increase the temperature of the atmosphere, which in turn kind of warms the Earth. That's the idea of it. And hence, the more greenhouse gases, the more the temperature of the environment is going to increase. Okay, let me talk you through a question. That was horrible spelling, but yeah, there we go. Just do the one from AQA. Yeah, they're all free. They're all freely available. These are all standard enthalpies, MZ. Okay, these aren't the questions I mean. Where are they? Maybe it's just in part 2. That's NMR spec. I'm sorry, I'm just trying to find these questions. In here. There we go. No, sorry, a lot of these are NMR questions. NMR spectra is an A2 concept, so I'm not really going to go through them today. But I don't know why I can't find them. Okay, I'm going to try from the OCR spec because I know that there are definitely questions like this in the OCR spec. Spectroscopy, part 1. Okay. Yeah, so this is the kind of question that you can be given an exam. There we go. So interpret this information. So it's an atmospheric pollutant. So highlight key information first. Fuel combustion of and diesel. Compound X, and I've been given percentages. I've been given an M plus peak, and I've been given a 1 to 2 molar ratio with hydrogen and nickel catalyst. So let's try and see what they're trying to lead me down first. So the first thing I'm thinking in my mind is I'm thinking, what are they going to try? What are they trying to get me to say? So this M plus peak gives me the MR. I know that already. This composition by mass, it sounds like they kind of want me to do an empirical formula, which I will be happy to oblige. And this 1 to 2 kind of tells me something. It tells me that 1 mole of X needs 2 moles of hydrogen to be hydrogenated. That tells me, it tells me that this molecule is going to have 2 carbon-carbon double bonds. That's That's the important thing that this tells me. Now, I've got all the information I need. Let's do an empirical formula first. So 88.89 to 11.1, divide this by 12. So 88.89 divided by 12 is, get my calculator out. 88.89 divided by 12 is 7.4 to 11.1, because obviously just divide that by 1. And then divide 11.1, divide that by 7.4, which is exactly a ratio of 1 to 1.5, which means that in its whole number form, the empirical formula is going to be C2H3. I'll explain that later. But now I know that it's C2H3. The M plus P tells me it's 54, so the MR is 54. The molecular mass of this empirical formula is 12 plus 12 plus 3, which is 27. 54 divided by 27 is 2, which means that the structural formula is C4H6. Kind of makes sense. Where did the 12 come from? Yeah, the 12 is the atomic mass of carbon. So again, if you want to find out about calculating empirical formulae, I've done that in a previous lesson. So again, if you go back over the recordings, there is that content on calculating empirical formulae. But structural formula is C4H6. Now, I've been asked to explain why this tells me that there is a 1 to 2 molar ratio, tells me that there is 2 double bonds. Basically, this reaction is hydrogenation. So if I see the words in an examination setting, I see hydrogen in the presence of a nickel catalyst, I think hydrogenation. And hydrogenation is the removal of double bonds by adding hydrogen across the double bonds. Quite simple. So hydrogenation, whatever our molecule is, C4H6 plus 2H2 has got to give me C4H10, which is an alkane. Now, if I'm adding 2 hydrogens, that means that there's got to be 2 double bonds in the original molecule that need to be broken to convert this original molecule into an alkane. Make sense? So C4H6, and then I can draw that in any capacity. Literally even just draw it like this. So now I've got 1, 2, 3. So that needs 1 here. This is going to have none. 1, 2. And there we go. C4H6. That's a potential structure for it. And remember, you've only been asked to deduce 1 possible structure for compound X. You don't need to deduce that much. So 1 possible structure is all you need. And that's kind of it. Let's do one more long answer question. Maybe let's see if I can find an actual one with spectroscopy on them. Maybe the long marker with spectra. No, not. Might be in here. Splitting patterns. Oh no, high resolution NMR. Kind of what we're talking about today. Yeah, this is a perfect question. So we've been given this kind of structure. We've been told that it's got a molecular formulae of C2O3H4. And we've been told that it's from skin compounds and it's got two functional groups containing oxygen atoms. We've been given an IR and a mass spectra. And the question is asking, it's basically split up this question to kind of indicate what it's looking for. What I can see from this peak here, so there is a broad peak at about, there's almost two broad peaks here at about 3,200 all the way down to 3,000. That indicates an OH group, indicating an alcohol, not a carboxylic acid. Quite important to note because, again, there is also a peak here at about 1,500. There's also a peak here. Sorry, that peak is part of the fingerprint region. This peak here, that indicates C double bond O, which means that we know, so there are two functional groups containing oxygen atoms, and there is also a third oxygen we're not thinking about here. So can anyone tell me what the third group might be, essentially? Why is there a third kind of oxygen atom here? Because actually there's been a bit of a trick that they've put in here. Anyone? Ketone or ether? No. I've actually kind of lied about this. If I draw that out, does that make it a little bit more, kind of make it easier to see it? Yeah, it is a carboxylic acid. There are actually two peaks in this one peak. So there's the OH indicating an alcohol, but then there's also a second peak that's an OH indicating a carboxylic acid. And they're two separate peaks. And the way you can tell that is because of this rise. Because it rises back here, that indicates that that's the end of one peak and the beginning of another peak. So this structure is actually probably more likely to be one, two, three, four, three O's and C. So that's kind of probably the most likely outcome of this image. And we can double check that because this question has actually given us the image. And yeah, so you can see that there is both the carboxylic acid group and the alcohol OH group. And again, that's because of two different broad peaks. Right. Does that make sense? Does anyone have any questions about all of that? Any questions? I'll go back to the one general question I got sent. Let me double check that. General question. With regards to revision, my school emphasizes general reading and going beyond the subject to get the best grades. How important do you think this is for someone who struggles to complete all mandatory work in revision? Well, the priority should always be the mandatory work in your revision. Again, you should be focusing on trying to kind of improve those. Again, over time, you'll work on those time management skills, and there'll be something that you do end up working on. But your school will try and emphasize that because it is a very important skill to develop to be able to read ahead on content. But your priority should be making sure that you're staying revised, continuing doing your exam questions, continuing your general structure of a week. What can I use to expand your reading for A-stars? I don't know. I get this a lot. This question comes out when people think that you need to be doing insane extra reading to get A-stars. I got 3 A-stars at A-level, and I didn't really read that much outside the subject, in the sense that I read the spec, you need to know your spec like it's the back of your hand. What you need to develop to get an A-star is adaptability. So it's all well and good knowing your spec. If I know IR spectroscopy works in this way, I need to be able to understand that. So when I say time of flight, when I talked about time of flight spectrometry, it will not be in any of your textbooks, it will not be in your spec telling you about the kinetic energy equation. But you need to be able to be adaptable and be able to bring in your knowledge from previous years, or bring in knowledge that you generally just know, to understand why things work in certain ways. Because often the A-star questions aren't going to be about how something works. They're going to be about why things work, especially when you look at both biology and chemistry. They're going to ask you a lot of why things work. I can't find the previous lessons recording on YouTube. I'll show you how to get to that. So I'll take you through. If I go into YouTube, I go into Study Mine. And I go on to, if I go into live, you will have all of the previous recordings from previous kind of lessons that we all had. So from all of there were 3 different tutors, you'll have all of the recordings, biology, chemistry, from all of the previous lessons. So you don't go into videos, go into lives instead, and they'll have all of the recordings from it. Cool. What A levels did I do? Biology, chemistry, and maths. Would I happen to do any physics lessons? No. Sorry, I didn't do physics at A level. No idea. Yeah, the idea is understanding is your key. If you understand why things work, you'll be able to put it into any situation. One of the things, if you come to any of my biology lessons, one of the things I talk about a lot is I talk about drawing parallels. And one of the things I found that was very helpful was to draw. I was a big fan of human biology, liked it a lot. I mean, I still do, it's part of my degree. But I wasn't really a big fan of animal or plant biology or plant physiology. But once I adapted and I learned to draw parallels between human biology and plant biology, it started making a lot more sense. So for example, understanding that the xylem is kind of like your trachea. So your trachea needs to be able to deal with high pressure. The xylem also needs to be able to deal with high pressure. And you can do that with chemistry as well, to try and draw parallels to understand why things work in certain ways. And that's kind of the best advice I can give you, is to understand, oh, wait, this makes sense. Which is why it's really important that you understand the basics of chemistry before you move on to understanding the more advanced content, because you build from the ground up. Does StudyMind offer any support for physics? Yes, there are amazing physics tutors that will be able to provide you with brilliant support for physics. Just, I don't think they would be in the purview of these lessons. Same with maths. They'd fall outside of the purview of kind of these free classes that we're doing. Any more questions? I know this has been a slightly shorter lesson. Again, it's quite a short topic. Next lesson will probably be a lot longer, because we'll talk about alkanes, alkenes, and alcohols. So there's a lot of mechanisms to it. So again, that lesson will probably take slightly longer to do. But if there are any other questions, feel free to say.